Hello everyone. In this virtual lecture, we're going to look at errors and exceptions. This is a topic that all of us are familiar with, possibly from or since the first line of code that we've written. And we're going to break down errors into two main categories. We're going to talk about syntax errors and also state or runtime errors. And before we dive into these two, I also want to address one additional type of error that we're all going to run into at one point or another, and that's called a semantic error. Now, a semantic error differs from these two in that it doesn't cause our program to crash. It's not going to cause for us to get any error messages. Semantic error is when our program does something other than what we intended for it to do. And because of this, semantic errors can also be referred to as logical errors or logical bugs in our programs. To demonstrate that, we have a quick and simple example here. We have a function called net worth check that takes in someone's net worth as, let's say, a couple digits, and based on that determines if they're a hundredaire, a thousandaire, a millionaire, and we capped it off here at a billionaire. And the way that's being done in this function is that net worth is being converted to a string, and then we're taking the length of that string to see how many digits are in the net worth provided by the user. And if the length of that string is equal to 3, then they're going to be a hundredaire. If the length of that string is between 4 and 6 characters, they'll be considered a thousandaire. If it's 7 characters, they're a millionaire. And again, we capped it off here at a billionaire. So let's say we wrote this program and then tested it. So let's pass in 1,000. We can see that it correctly categorized us as a thousandaire. Let's run this a couple more times. Let's pass in, let's say, 507. Yep, it told us we're a hundredaire. Let's pass in a million. It told us we're a millionaire. So if we were asked to write a program like this and we wrote this function, we might be pretty happy with it at this point, and we might give it back to the individual that asked us for it and say, it's ready to go. And then it might work fine for a little while. And let's say someone comes along and they just graduated from medical school, so their net worth is not a positive number, it's actually negative $200,000. So they come in here and check, and they're told that they're a millionaire, which is sounds wrong for a couple reasons, right? Obviously, they have a negative net worth, so they shouldn't be a millionaire. And to be a millionaire, here we're checking that the net worth has 7 digits. And if we look at 200,000, we can see this number is composed of 6 digits, and we're preceding it with a negative sign. So when we convert this entire number to a string and take its length, it's going to have a length of 7. So here we're incorrectly identifying someone as a millionaire. Let's say someone says they have $10,000 and a penny, and we check their net worth. Now we're being told that this person is a billionaire because we have 1, 2, 3, 4, 5, 6, 7, 8 total characters, right, in this net worth that's being passed in, and they're being considered a billionaire because maybe we didn't expect for someone to include a decimal followed by cents. So these are examples of semantic errors or bugs in our program that we might not identify right away, depending on how thorough our QA testing is and how far we explore edge cases or maybe inputs that we wouldn't expect to get when originally developing our program. And arguably, these are the worst types of errors to have because, as you can see, our program doesn't crash. We don't get back any error messages. It just doesn't work the way it's intended to work, and it could take a long time for someone to identify these errors. And even if we identify an error early on, it could take a lot of effort and debugging to identify where in a program that error is actually occurring and how to identify it and to correct it. So those are semantic errors. And for the rest of this lecture, we're going to look at syntax errors and state errors. And we have a couple examples of those right here to the right. So the first statement we have here, we're trying to assign what looks like a string to variable excuse. And we can see in the string, right, we have this single apostrophe, which looks like a single quote inside of it. And because the string is limited by single quotes, as we saw from our string lecture, this is going to cause a syntax error. To address this, we either have to delimit our string by double quotes or escape this apostrophe, so it's not being treated as a delimiter for our string. This is causing a syntax error. Our program or our statement here is grammatically or syntactically incorrect. This next example here, we have a print function, and the expression inside this print function is saying hour plus colon plus minute plus colon plus second, and we see we get back a type error, and we're told we have an unsupported operand plus or addition between integers and strings. So we don't have the rest of the program in this case, but we can assume that our minute and second are variables that have integers assigned to them. And here we're going to run into a problem because we're trying to add integers and strings together, and this is going to cause an erroneous state of execution of this expression and cause a type error. Likewise, in this last example here, we're trying to open this file sample.txt. In this case, we're providing a relative path to this file, which means that we're expecting for it to be in our current working directory. And because we don't specify a mode for it to be opened in, it's going to be opened up in the default mode of read. And we know that if a file doesn't exist in the folder that we're pointing to, and we try to open up in read mode, we're going to get back an error. In this case, a file not found error telling us sample.txt does not exist. So let's take a look at syntax errors a little bit more in depth here. We can see that syntax error is a Python statement that's not correctly structured, right? So the grammar of our code is not correct. And what's important to realize is that these are detected while our interpreter actually translates our code into machine language before our program gets executed. And that's pretty important to identify, and we're going to look at an example here in just a second to demonstrate that. So there's a bunch of examples here of syntax errors, and you guys could probably peruse through these and identify why all of these are syntactically and grammatically incorrect. And we can see that for the most part, when we get back a syntax error, we're just told, hey, you have a syntax error and you got invalid syntax. If we copy one of these as an example to a shell, we can tell this is incorrect because here we have an opening parenthesis and a closing square bracket. If we run this, we can actually see the square bracket gets highlighted because this is where the interpreter identified the syntax error is. And we got back a very generic message, hey, you have invalid syntax. In some cases, like if we take this example here, we're trying to print out the string hello world and we see that we're missing our parentheses. We're actually getting back a more verbose message for the syntax error, which is pretty nice to see. It's not going to be quite as often as this generic message, but it's you're going to be able to see that for a couple examples. Now, again, syntax errors are identified before a program actually executes. So let's look at an example here. In this program, we're assigning 1 to x. We're going to attempt to print out the value of x, assign 2 to y, print out the value of y, add x and y together, assign that to z, and then print out the value of z. But as we can identify here, we're missing a comma in our print function here to separate the string and this int object that we're trying to print out. So this is going to give us back a syntax error. So if we save and run this, you can see that we got back an error, invalid syntax. And notice we have nothing in our shell, which tells us that our program didn't run up until this point, and then it caused an error caused it to stop, a syntax error, right? It didn't run in the first place, because if it ran in the first place, this would have worked. We'd assign 1 to x. This would have worked. We would have printed out x equals 1. This would have worked. We would assign y to 2, or 2 to y, I'm sorry. And then only at this point would our program stop running and identify that we have a syntax error. Because we see no output, this shows us again that these syntax errors are identified prior to the execution of our program while our code is being translated into machine code. Now if we jump to the next slide, we're going to be able to look at a bunch of different types of state errors. So we can see here a state error, as opposed to syntax errors, occur during runtime. And when a state error occurs, an error object gets created. And these error objects have a type of error and also information about the error that occurred. In this example here, we see we're trying to convert the string 4.5 to an integer. We get back some angry red text, so an error occurred, specifically a state error. We can see the type of error, it's a value error, as well as some information about that error. We have an invalid literal being passed to our int function of base 10. 4.5 is not a valid int literal in order for that string to be converted to an integer. And we can see the default behavior when we run these state errors is to print this information out to the screen and to crash the program, right? To interrupt its execution. We have a bunch of different examples here. In this next one, we're trying to divide a number by 0. That cannot be done. So the type of error that's occurring is a 0 division error. We can't divide by 0. Here we get back a name error because we're trying to evaluate a variable that hasn't been defined yet. An index error is one we're very familiar with when we try to access an index outside of the range of the accessible indexes in a sequential object. And this last one here, we're trying to multiply a list and list together, and we know from lecture 2 that we can all multiply lists by numbers. And likewise, the same thing with strings, we can multiply a string by an integer, which would concatenate that object to itself n number of times. Now, these error objects that are created are called exceptions, and the creation of an exception due to an error occurring is called raising an exception. Now, let's look at an example of when an exception occurs. So we said on our slide that exceptions occur during runtime. So here we have a very similar program to the one before. We assign 1 to x, print out x, assign 0 to y, print out y. Then we call our input function, and we know the input function pauses the execution of our program and waits for input to be entered by a user and for the user to hit enter afterwards. And after this input function executes, we see that we're trying to divide x by y and assign that value to z. Except at this point, x will have a value of 1, y will have a value of 0, or we're going to try to divide 1 by 0. That shouldn't be able to be done, right? We're going to get back a zero division error. So let's actually look at what happens. Let's run this. And we had a syntax error in here. So notice our program didn't run in the first place because we're missing a comma here. So we had a syntax error. I forgot that I put that in there. Let's save and run this again. Now what happens? Well, our program ran and now is hanging on at this input function. It's waiting for us to enter something and hit enter. What did it do so far? It assigned 1 to x, it printed out x equals 1, assigned 0 to y, printed out y equals 0, and then we have this input function that paused the execution of the program for dramatical effect. And now, if we hit enter, the next line of code that's going to get executed is this, where we try to divide x by y. And notice what happens at this point. An exception occurs, so the default behavior is to crash the program and print out the error object information to our screen, telling us that in this Python file, at this location, on line 11, this particular line of code, a zero division error occurred when you try to divide by 0. But notice, this occurred during runtime, so part of our program ran and only crashed when it reached that one expression that caused the exception to occur, versus when we had the syntax error and we try to run this program, the program didn't run in the first place because these are caught and identified prior to the execution of our code. So that's a big differentiation to be able to make between state errors or exceptions that occur in our code and syntax errors. One occurs prior to runtime and one occurs during runtime. Now on this slide we have a bunch of different types of built-in exceptions into the language. The first one here is a keyboard interrupt exception, and we could look at an example of this. Let's say we have code that looks like this. Let's say we have x that has a value of 1, and we have a while loop that loops as long as x is greater than 0. And inside the loop here, we're going to print out the value of x, and then we're also going to take x and increment it by 1 every time we loop. So if we look at this, we might be able to identify that we have an infinite loop at this point. If we run this, we can see that we do indeed have an infinite loop. And if we want to stop this, we can either exit out of our shell, open up Task Manager and close this process, or we can cause our program to crash by throwing an exception, specifically in this case a keyboard interrupt exception, by hitting Control-C. So we caused an exception to be thrown, right, during the runtime of this program, and the default behavior is for that to crash the program. So here we used a keyboard interrupt exception. Overflow error, we might not have seen this yet this semester. We see it's raised when a floating point expression evaluates a value that is too large. So maybe to demonstrate that, let's take something like 2.0 and try to raise this to the 10,000th power. And we see that the result of this operation is too large of a floating point number here, so we get back an overflow error. Notice that if we do the same expression with an integer, we don't get back an overflow error. However, it is possible to get back a memory error if the output of this expression is too large of an integer object. I'm not going to demonstrate that now so I don't crash my system. We have zero division errors, which we've seen previously. Found not found error, we've seen on the previous slide. Index error, name errors, we're all familiar with these. And we see we also have type errors and value errors. And again, these are two that we've seen pretty often, but we're going to look at some examples of them again. So a type error occurs when the type of object we're using in an expression is not the right one that we should be using with a particular operation. So for example, let's say we have a string here, the string a, and we try to say a plus 1. We know that we can't add strings and integers together because Python can't implicitly type convert between the two of these. So we get back a type error due to the type of object we're working with, and we're told we can only concatenate strings to strings, not integer objects. However, let's say we take this expression and flip it around, and now we say 1 plus the string a. we still get back a type error, as we likely would have expected, but notice the message is slightly different. Unsupported operand type for plus, for addition, between an integer and a string. So these are both causing type errors, and they look basically exactly the same, except we see the informational piece of this is a little bit different. What's happening here is we have a string object. We see this plus sign here, which is being interpreted as a concatenation operator. We're trying to concatenate something to a string, and it's failing because we can't concatenate integers to strings. We can only concatenate strings to strings. Versus in this expression, we have an integer and the plus sign, which is being interpreted as the addition operator, and we're trying to add something to an int. In this case, an object type that's not supported, we cannot add strings to integers. So even though these expressions look basically the same, they're causing the same type of exception to be thrown, the underlying reason is different. So it's good to get into the habit of reading the error messages that we get on our screens and really understanding what's causing them to happen. Now, a value error, I think the best example of this was shown in the previous slide. Let's say we try to convert a string to an int. It can do that, right? We know we can convert strings to ints as long as the int or the string contains a valid int literal. If we try to convert 4.0 to an integer, we see we get back a value error because we don't have an int literal as the value for the string. Notice, this didn't crash because we're trying to convert a string necessarily to an int. It crashed because of the value that the string has. So again, sometimes the difference between a type error and a value error might be small, but it's important to be able to identify the differences between these two, and being able to do so will definitely help us troubleshoot our code in certain scenarios. Now, we saw on the previous slide here that the default behavior when an exception is raised is to crash our program and to print out the exception. However, we might want, in certain circumstances, to be able to handle our exceptions, and we're able to do that by using what are called try-except statements. If we've programmed in other languages before, we might know these as try-catch statements. In Python, they're called try-except statements. So we're going to come back to this example in just a second. First, we're going to jump to the next slide here to look at the syntax. It's very familiar to basically all types of control structures we've been using so far this semester. So the way try-except statements work is that inside of our try block here, we want to have an indented block of code, and this is the code that could potentially cause an exception to be triggered. And what happens is, if the code indented underneath a try statement causes an exception to be raised, instead of Python following the default behavior of crashing the program and printing out that exception, it will instead transfer execution to the except statement and execute the block of code underneath this except statement. And this except statement will basically be handling the error for us in a way that we define. And then after that's done, we simply continue executing the rest of our program by going to the next unindented line of code in our program. And to really demonstrate that, let's look at an example, because that's going to visualize it for us, and it's going to make more sense than probably what I just said. So let's open up an editor, and let's put this code in here. So if we save this as try-except, so our desktop. So we can see in this code here, we're asking someone for their age, we're converting that age to an integer, and then we're going to simply print out, you are that many years old. And we've written this code before. Let's run it. Let's type it something like 15. And it worked basically as expected. But what happens if we run this, and instead of giving a numerical age, we write out or spell out our age, 15. At this point, what happens? Well, let's look at our error. So we could trace it back to this program, try-except.py, the second line of code in that program. Here, when we're trying to convert string age to an int, we get back a value error. Right now we understand exactly what this means. We have an invalid literal for the int function. We're trying to convert the string 15. 15 is not an int of base 10. And again, we've done this example prior, so we understand why we get back this error. So what can we do here? Well, instead of having our program crash under these circumstances, how about we use try-except statements to handle this error and not have our program crash. So the code that contains the expressions that could potentially cause an exception to occur goes underneath our try block, or our try exception statement here. And underneath our except statement, we put the code we want to execute if an exception occurs in the previous code. In this case, we're going to print out a message that says enter your age using digits, as in don't type it out. So now let's save this and try to run this. If we type in 15, as we did before, you can see it works just as well as it did then. Let's trace through our program. So here we asked the user for their age. We entered 15. 15 was converted to an int and assigned to int age, and then we printed out you are this many years old. And at that point, because we reached the end of this try block and no exceptions occurred, we simply break out, skip the except statement, and go to the end of our program. And to demonstrate that, I'm going to just print out the string done. Now let's run this again. And in this example, let's pass in 15, which previously caused an exception to occur. So now let's try to determine what's going to happen. So we just ran our program. This line of code executed. It asked us for our age. We typed in 15. Once we hit enter, we're going to move on to this expression here, where we're going to try to convert the string 15 to an int. At this point, as we saw before, a value error is going to occur. However, now because we're inside of a try block, we're going to jump to the associated except block. Instead of crashing, we're going to execute the code underneath this except block. So instead of crashing and printing out this exception message, we're simply going to go to our except statement, print out, enter your age using digits. At that point, we're done with our try except block, and we simply go to the next line of code in our program, which will print done. So let's see if that happens. And it did. Again, now instead of an exception, right, being thrown to our screen, we handle that exception gracefully by simply printing out a message here in our except block, and then when we're all done, we print it out done. To make this program a little bit more robust for this example, let's use a while loop. Let's say a while true loop. And what this is going to allow us to do is to continue looping, right, and handling these exceptions until we get some good input that doesn't cause an exception to be raised. And we're going to put a break in here to make sure that eventually we do break out of this loop. So let's run this. Let's say we enter 15 spelled out, which we know is going to cause an exception, and that exception gets handled. But now, because we're inside of a while loop, our program doesn't terminate. We went to our except block, we printed out our message, and now we go back to the top of our while loop and we keep executing. So let's go ahead and type in another age that will give us an error. Let's say we type in 15.5 because we're 15 and a half. Again, that can be converted to an int to cause an exception to be raised. We handle the exception and we keep looping. If we type in a valid input, which will not cause an exception, we'll print out you are 15 years old. Afterwards, we'll hit the break statement, which will break us out of our loop and take us to this print function, which will print out done, as we can see happened here. Now, if we jump back to our slides, we can see here that we can actually specify or restrict an except statement to catch exceptions of a specific type. And we can do that by specifying the exception type in our exception statement. So here, if we go back to our example, we see the exception that we've been triggering or throwing is a value error exception. So if we come to our except statement, we can restrict this except statement to only handle value errors. Now if we save and run this program, we should see it should operate exactly the way it did before, because we have been triggering value errors, and we can see that not much has changed. However, what happens if we cause a different type of error to occur? What if we cause a keyboard interrupt error to occur by hitting Control-C? Now we see this keyboard interrupt error wasn't handled because our except statement here is very specifically only looking for value error. So at this point, our keyboard interrupt caused our program to crash as it normally would. If we go ahead and change this to look for keyboard interrupt errors, let me just copy it from here. Now we'll see that since it's turned purple, we can run it and we can handle keyboard interrupts. I'm just hitting Control-C. However, now if we cause a value error exception to occur, that cannot be handled because we did not specify that in our except statement here. What we can do is we can have multiple except statements. So let's say here we have except value error. Let's put another except statement here. And this except statement is going to look for keyboard interrupt errors. We'll print out, you hit Control+C. And let's run this. So now if we type in 15.0, we see that we caused an exception or value error to occur here. So we jumped outside of this try block. We went to our first except block here, and we see here that this is meant to handle value errors. Because 15.0 caused the value error to occur here, this except statement is what handled it, and it printed out enter your age using the digits 0 through 9, and that's the output that we had. At this point, we skip this except statement, we go back to the top of our while loop, and we try again. Now, instead of causing a value error to occur, how about we try to cause a keyboard interrupt exception to occur by hitting Control-C. Notice it was handled, right? It didn't crash as it did up here. But notice the message we get back is a different message. Now, at this point in time, when they're asking us for our age, we hit Control-C, which caused a keyboard interrupt exception to occur instead of our try statement. So at this point, we break out and we try to handle it by going to our first except statement here. Except here, we see we only handle value errors. So because this keyboard interrupt wasn't a value error, we go to the next except statement here and check. Will this handle it? Well, this one is specifically made to handle keyboard interrupt errors, so it will handle it. And notice now we print out, you hit Control-C versus this other message because this is not the except statement that handled this particular exception. If we wanted to, we could put another except statement here, and this one we could leave generic, so that way it handles basically any types of errors that occur. So let's just print out an error occurred. We're being very generic here, and again, we're doing this so that way we handle this error versus causing our program to crash. And to demonstrate that, let's just take our age and let's divide it by 0, just to force a 0 division error to occur. We know that this except statement can't handle it, this except statement can't handle it, so what's going to happen is we're going to get to this last except statement here, which is generally configured to accept any type of error or exception, and we're simply going to print out an error occurred. So let's run this. Let's type in valid age 15. Now we see that we got back that message, an error occurred because we got back a 0 division error at this point. This couldn't handle it, this couldn't handle it. This last except statement was able to handle it. And we can expand this a little bit more. We could actually capture the informational piece of this exception by writing exception as some variable. Typically, we might use the variable e. And let me go ahead and include e in this message that we're printing out. So let's type in 15. So here we see that our message, an error occurred, was printed. And then we have a little bit more here, division by 0. So when we add this to our except statement, exception as something, we're able to capture the informational part of the exception and include it in our error message. So again, at this point, you see we gracefully handled this exception by making our program not crash, and we got back the same information as we normally would have if the program would crash. So kind of a long example here, but we have all the pieces that we would need, right, to make our program pretty robust in terms of error handling. Okay, so here we have another example. Let's look through it here. We're defining a function called readAge that's taking in the name of a file. It's attempting to open up that file in the default mode of read. Afterwards, we're going to read a name or a line from that file, that string age, try to convert that age to an integer, and then print out what the age is. And notice we have this inside of a try except block because we could potentially have a value error occur when we try to convert string age into an integer. So what happens if in our file we have the string 15 rather than the number 15? At this point, when we try to convert 15 to an int, we're going to get back a error or an exception, specifically a value error. Now, if we run our code and we pass an age.txt, which has this inside of there, we can see that that error, that exception gets handled. Instead of crashing, it's going to print out value cannot be converted to an integer. However, look at this next example here. What happens if we try to open up age.txt, but age.txt, or in this case, I'm sorry, it's text. Notice we misspelled the name of the file or the extension of the file. This does not exist in our current directory. So now an exception is still going to occur, except it's going to occur now instead of on this line of our code, it's going to occur on this line of our code. We're going to try to open up this file in read mode. Because this file age.text does not exist in the current working directory, we're going to get back a file not found error. And notice this error does not get handled, or this exception does not get handled, because our except statement is configured to specifically look only for value error exceptions. So how can we handle that? Well, we saw in our previous example, we can have more than one except statement, each of them looking for a specific type of exception. And the reason we might want to do this is because now we can print out messages very specific to the exception that we're working with, right? It doesn't have to be something generic. And again, that can make our code a little bit cleaner, or our program a little bit more robust. And we can see here that we can additionally, in our except clause, include more than one type of exception that we want to handle, and have them be handled the same. At this point, I'm going to leave this last example as an exercise for you guys to go through and type in and kind of play around with to make sure we really get a grasp on how we can use try except blocks inside of our code to handle exceptions. So with that, thank you for your time and happy practicing.